Okay, so we can start the last theoretical lesson of the course. Then we do only the practical, the hands-on lessons. Okay, let's talk a little bit about tilted accretion disks. So far we discussed a lot the Shakura-Sunyaev disk. We found some solutions for temperature and density profile. However, everything we did so far was for a disk parallel to the equator of the black hole. But let's be honest here, this is the rarest case of accretion that we can find. Imagine that accretion, a cloud to be accreted, or a star that will be disrupted and then accreted by the black hole, will come from any direction, right? So the situations that we studied so far are the special case. In a more realistic scenario, we have tilted accretion disks and a sort of nice relativistic effects appear in this situation. For instance, in this simulation here, this was done by Liska et al. This is part of the group of Sasha Chekhovsky professor. And in this simulation, we have a black hole with the spin axis in the vertical, rotating at 0.94. The maximum rotation, this is the adimensional rotation, is 1, okay? So this is almost at maximum rotation. And you see that the disk will start to precess, and it will break in this precession. And this precession comes from this effect that we call the lane steering effect, which is the precession of the orbits dragged by the metric around the black hole. Okay, let's take a look on a simulation, because at this point we are not doing equations anymore. Okay, if you want. Okay, let me stop it here. Okay, in the very beginning. Okay, so just bear this in mind, how this is the 2D profile on the right, and this is the 3D scheme of the disk. Just bear in mind that we started with a disk like this. This is our initial condition for the simulation. And look what happens. Okay. So the disk already broke, and it's quickly absorbed by the black hole. And you see that the disk starts to break in several pieces. The internal pieces precess much faster. The outer disk here is also precessing. Okay, it breaks and absorbs, breaks and absorbs. And at some point you notice the appearance of another general relativistic effect called the Bardeen-Peterson effect. It will appear in a while. Okay, here we have several disks precessing. They look like wings in the right now, but it's just the precession, the 3D precession. Okay, here, can you see that the disk is aligned with the black hole equator at this point? It's quite stable. This is what we call the Bardeen-Peterson effect. It's the alignment, the forced alignment of the disk with the equatorial plane of the black hole. Okay. Okay, let's go to the...
So this effect is just for, as more, it gets divided into two disks, right?
Yeah, so... Is more what? Only the inner part of the disk. In some, depending on the viscosity of the disk and on the inclination. Now it's very stable. And on the inclination angle, it will not even break. The disk will just bend. Okay, and the very inner part will rotate together, will align with the equator of the black hole, while the outer disk will never align. Okay. Okay, I have another one here. This is for the Bardeen-Peterson effect. And over time, so this time again, the spin of the black hole is in the vertical. And if the disk is tilted, over time, the influence of the disk in the black hole can make the spin axis of the black hole change, okay? Just to conserve the momentum of the whole system. So we have the angular momentum of the disk and the angular momentum of the black hole, which is typically much, much higher, much larger than the angular momentum of the disk. But the disk can affect the angular momentum of the black hole, pushing it towards the direction of the total angular momentum. Okay, so we can they can influence each other. So here we see the lane steering again and Bardeen-Peterson again. But this is a simulation by another group. See, here the disk is not even broken, and the accretion is already aligned. Now, okay, now it breaks. This one is really, really cool. I wonder if this is really possible to see something like that. The evidence from simulations support this, no, but in practice we never measured. Okay, now here we have the Bardeen-Peterson effect. You see that the central disk is very stable and aligned with the equator of the black hole, while the outside ring-like disks are precessing. You see that the closer to the black hole, the stronger is the precession. Okay. And the last simulation I show you, again by Liska. Liska is the one that did this first one here. And it's basically the same thing, but when we include relativistic jet that I briefly mentioned to you on the last class. So we have an inclined disk and a jet. The one thing I don't understand very well is how this jet is collimated here, because it looks like it's the collimation is guided by the accretion disk, and I'm not sure if this. Oh, okay. Can you let me just go back a little bit? Yes, you see that the jet is going to obliterate the outer disk. The expectation is that if such a thing happens, we would observe a lot of emission in high energies like gamma rays and X-rays. But even though we observe a lot of variability in gamma ray-like curves of active galaxies, one thing is observing the variability. Other thing, completely different, is saying that that variability is due to this kind of phenomenon. No? So there is quite a consensus that the jet will always be launched from the poles of the black hole, but this is not the case here, no. So I could not find the details of this simulation, but I'm showing you anyway, just because I think this one is really cool. Okay, but we have for sure we expect some feedback from the disk orientation in the jet direction, but I just don't know how much the disk affects the jet. Okay, the orientation of the disk affects the orientation of the jet. Okay, Let's talk about the Blaine-Ford-Snedek process. This is a mechanism that allows particles to steal energy from a rotating black hole. Okay, so if we don't have rotation, we don't have jets in the black hole. And the particles accelerated in the jet, they have to take this energy from somewhere. And most of this energy comes from the rotation of the black hole. Okay, so the power of the jet is proportional to this is a dimensional spin parameter of the black hole. So it depends strongly on the rotation of the black hole, it goes to square. Depends on the magnetic field, so the larger the magnetic field, the stronger is the jet, and depends on the mass of the black hole. So this is already something very interesting. So the strongest jets will come from the fastest rotating black holes and the most massive ones. Okay, so typically black holes in the center of giant galaxies, which are those monstrous black holes, they have the potential to launch very, very powerful jets. Okay. There is a confusion. One of the students asked me in the first class, maybe, or the second, about how these strong magnetic fields are kept over such large distance. But actually, they are not strong. The magnetic fields in a quasar blazar jet are of the order of 0.1 Gauss or 1 microgauss. If you get closer to the black hole, they can increase, but for a supermassive black hole like the one in Messier 87, the expected maximum magnetic field around the black hole is just a few hundredths of Gauss. Okay, so it's not an absolute. If you decrease the size of the black hole, you can increase the magnetic field. But anyway, in the jet, the magnetic fields are quite small. However, they extend over kiloparsec scales. Okay, so you have time and space to accelerate the particles. Okay, this was Hercules A, a very, very famous radio galaxy. Have you heard about the Fanaroff relay dichotomy? Have you ever heard about it? You, Anna. Francesco Massaro published a lot of things about Fanaroff relays. And I think also one catalog called the Freycat. Fanaroff relay galaxies. Yes, about it has to do with the morphology of the jets. So, or the lobes. Yes, plumes or lobes. So the basic picture is this one here on the right. So this first panel on the left shows us a Fanaroff relay type 2, and this on the right is a Fanaroff relay type 1. This is convention, but this also separates a lot of the physics here. So these guys here, the Fanaroff relay 2, they have very powerful jets that can drill through the intergalactic medium. Okay, so what defines if we have a Fanaroff relay 2 or 1 is the power of mainly the power of the jet and the density of the environment. So you can have a powerful jet, but if the environment is too dense, it cannot effectively drill through this environment. Okay, and then you have something like that. How do I say jato amortecido? You know, and well, this other here, no. So here we have supersonic jets drilling the gas, and in the other case we have what we call transonic gases, transonic jets, trying to drill and failing to drill the environment. Okay. Okay, so the typical characteristics of Von-Neurath relay class 1, this one here. So they are, in terms of morphology, they are center brightened. You see that they are brighter here, close to the black hole. The Von-Neurath relay 2 is the opposite, okay? The jets of Von-Neurath relay 2 are Von-Neurath relay 1, I'm sorry, are subrelativistic or transonic, and they tend to decelerate quickly and plume out like you see here, like a candle flame, no? And they also have a lower luminosities. And here, by convention, lower luminosities are below 10 to 25 watts per hertz per sterradian. Okay. For the Von-Neurath relay 2 case, we have the edge brightened morphology, so you can see here, and the brightest points are in the edges of the lobes. We have these very bright radio lobes. This is where they hit the extragalactic medium. So we have a change in density of the environment, and they remain really relativistic, and they are supersonic until they terminate in the shock, and they are much brighter as well. Okay, so by convention, brighter than 10 to 25 watt per hertz per sterradian. Yes, this is a summary of what I told you. So the Von-Neurath relay 2, the jet power is high enough to drill through the environment without losing its speed until it reaches the edge of the lobe, which is where you have a change in the density of the environment. Yes, this is just a summary of what I said before. By the way, you see that in this class I put a lot of things together, and some of them are not well connected, because these are the remainings of what's very important to know about AGNs. Okay, so I'm doing a sort of a soup in this lesson, but this is the closure soup. Okay, so you have to gather this this information just because you hear this a lot if you are doing AGNs. Okay, so most giant elliptical galaxies with jets are Von-Neurath relay 1. Do you remember which galaxy is this one? This is a very famous one. Valen Trespo. No, Valen nada. This is a very famous one. M87. Yes, Anna is amazing. Anna is amazing, no? Anna is amazing. Messier 87. And okay, you see that most of these giant galaxies, Messier 87 it's the main galaxy of the Virgo cluster. Okay, it's a giant galaxy with a black hole with a few, I don't remember exactly, but it's like a few billion solar masses. It's really, really huge. And in these galaxies, the tendency is that the jets are going to be of the Von-Neurath relay 1 type. And do you have a clue why? We have larger black holes. These black holes have strong jets. The jets should drill through the environment. But in this case, they don't. We have Von-Neurath relay 1 here. Just bear in mind that this kind of galaxy you can find typically in the center of galaxy clusters, where the intergalactic medium on average is denser. Okay, so even if these jets are powerful, they find it difficult to drill their way because the environment is dense. Okay. When a black hole is accreting a lot of gas, for instance in the Shapura-Sunyaev disk, its disk is very efficient in anchoring strong magnetic fields and leads to high power jet that can potentially, not always, become a funnel related to kind of jet, which is not the case for. Actually, Messier 87, we don't have a Shakurosnev disk. It's more to a Ryaf than a Shakurosnev, but anyway. Have you heard about the M sigma relation? This is already disconnected, but I have to show you. Have you ever heard about the M sigma relation? This is something you hear everywhere, not only in Asian physics, but in everything in extragalactic astronomy. You heard about it? Mm-hmm. Of the stars in the Bouge, in the Bouge. Yes, but we don't know exactly why this happens, especially because the gravity, the force of gravity of the black hole, the action of this force in the Bouge is negligible. Once, a few years ago, I saw a colleague of mine doing an outreach video saying, did you know that the solar system is orbiting a black hole in the center of the Milky Way? Do you think this sentence is true? I told you. You got what I say, right? The sentence was, did you know that the solar system is orbiting a supermassive black hole in the center of the galaxy? In the center of the Milky Way? Is this true or not? Maybe the question is a bit, I admit it's a bit, we should define better the things. But, but actually, if, let's say, I was about to say we remove the stars. But no, let's go direct to the point. The gravitational influence of the supermassive black hole in the center of the Milky Way at the position of the solar system is zero. It's 0, 0, 0. Okay, it's absolutely negligible. Actually, the influence of the supermassive black hole in the center of the galaxy is already negligible at the bulge of the galaxy. Do you know what I'm talking about? What is the bulge? What is the disk? Okay, so in a giant galaxy like the Milky Way, we have the black hole in the center. We have the bulge, which is this spherical ellipsoidal structure around the center of the gravity center of the galaxy. And then in the case of a spiral galaxy, we can have the disk. This will be a flatter part of the galaxy, okay? So black hole, bulge, and the disk. So in the bulge, which is already this internal structure, the influence, the effect that the gravity of the central black hole causes in the stars in the bulge is zero. Okay, the bulge is already so big that it should not be influenced by the gravity of the black hole. Okay, so this is a bit a mystery. Why we see this correlation? It's very likely related to the dynamical heating. Is something that maybe we can discuss in another moment. Some days ago, I showed you, we discussed about the gravothermal collapse and the globular clusters, right? This dynamical heating can happen in globular clusters as well. So it's likely something related to the dynamics of the system. It's not directly related to the gravity attraction, the gravitational force of the black hole. Okay, so going back to the sentence, did you know that the solar system is orbiting a black hole in the center of the galaxy? This is equivalent for you to put an olive in the pole of the sun and say, did you know that the Earth is orbiting an olive in the center of the solar system? It's basically the same, okay? So it's negligible, it's there. So we are going around it, this is true, but it's not because we are attracted by it exactly. There is a lot of mass in the galaxy inside the orbit of the solar system. So the pull of gravity that the solar system feels is the pull of gravity of everything it contains. Okay. Okay. So if someone tells you that we are orbiting a black hole in the center of the galaxy, be aware. Okay. So we have this correlation. So the correlation is well established. Yes.
But the gravitational effects of the black hole is negligible in the bulge, not in the disk.
No. I said that it's already negligible in the bulge. In the disk, it's more than negligible. Okay, it's 0, 0, 0. Okay, so the solar system is in the disk. So we are orbiting the galaxy, but because we are being attracted by everything inside the orbit, not exactly just by the black hole. Okay. So yes, the pull of gravity of the black hole in the bulge is small, and it's basically 0 in the disk. Okay. Okay, so the correlation is very well known, but the cause of this correlation is a matter of discussion. Okay, it's very likely related to the dynamical heating, but it's likely, it's not proven. Okay. Okay, this is fine. By the way, do you know what is stellar velocity dispersion? No. This is important to say, no, because I was talking here like you all knew about it. Vai Anna, tu che sai tanta cosa. No problem, huh? But it's the same effect that we see in the broad lines in AGN. When you measure when you measure the width of the line, you are measuring the dispersion velocity of the gas there. If you have a cloud of gas going, here is the black hole, the cloud is going in that direction, the line it will emit will suffer from a little bit of Doppler redshifting, and then it will create an elongated wing in the line towards the red. Okay, other cloud that is coming in this direction will create a wing in the line towards the blue direction. Okay, imagine we have 300 clouds. They are randomly moving around the black hole. Now the width of the line that I measure is actually the dispersion. It's not the specific velocity of each cloud. Okay, it would be better if I could do that, if I could measure the velocity of each cloud. But no, I can only measure the typical speed of the population, okay, around the black hole. In the case of stars, we can, for instance, do a redshift campaign on several stars in the bulge, for instance. And you can see, this star has a little bit of blue shift, this other has a little bit of redshift, and then you do that, let's say, for 1,000 stars. You have a distribution of speeds, okay? And the sigma of this distribution will be your dispersion velocity, okay? So you are not taking the speed of a particular star, you are taking the typical speed of the population, okay? Okay, but let's take a look on what are the typical host galaxies of blazars? Look, I'm talking about blazars, not AGN in general, okay? So they are typically giant elliptical galaxies. And we have very large black holes in these galaxies. They are typically found in the inner parts of galaxy clusters. And these black holes towards the center of the cluster tend to be the black holes which had passed through most mergers. Okay, so we have several mergers of smaller black holes, creating these large black holes. So why elliptical galaxies? Supermassive black holes. So if the mass of the black hole is large, the jets will be more powerful. And of course, the M sigma relation ties these black holes, the most massive black holes, with the largest spheroidals. These galaxies are basically large spheroidals. No? And jet formation favors high black hole spin. And I just mentioned that these black holes, we think that they grow much faster through major mergers. So mergers of two or more black holes, okay? So if you have two black holes coalescing, the final rotational speed, the final angular momentum of this system will be very large, okay? So you have massive black holes which are likely spinning really fast, okay? These are excellent ingredients for launching jets in the case of blazars. And the preference for ellipticals is not universal through all the AGNs, okay? For instance, the Seyferts typically happen in spiral galaxies, okay? Blazar, again, on the host galaxies, I just told you that most of the blazars, by far, are in elliptical galaxies. And there are some cases where we have this quite weird spectra. If this was a normal elliptical galaxy, we would expect the spectrum to drop really fast here after what we call the Gaussian to HNK break. It's the Gaussian break, okay? So we would expect this to drop really fast. In this case here, it doesn't happen. We see that this galaxy, which looks like elliptical up to here, suddenly it has some blue continuum, which is quite high. And we do a clever trick here, a very straightforward. We simply measure the flux before and after the Gaussian break and measure this coefficient here. If it's below 4, indicates that we have significant non-thermal contribution. What I mean by significant is that we cannot explain this contribution by any means with stellar emission, okay? So this number, this precise number 0.4 is actually a convention, okay? But it just means that we cannot explain it with stellar emission. Okay, this will be very useful for you. So see, just this coefficient. This kind of galaxy we call, depending on the catalog, we call it BZG, which is a blazar of galaxy type. Okay, it's just we have a hint of a blazar emission there. By the way, most of these cases we cannot resolve the jet. So you look at the galaxy, it's a point-like source. You take the spectrum. It's not like the Messier 7 where you see the jet. You have a point. So you take the spectrum and you have to extract conclusions from them. Okay, so probably it's a very small jet, probably hidden in the inner part of the galaxy. Okay. Dusty Torus. The Dusty Torus, I remember that you two drawn the Torus during the exam, right? At least you drawn it. You tried. Maybe you draw. You tried to. Yes. One thing that we were doing there was sort of considering the Torus as this sort of dust cloud, no? More or less homogeneous. Okay, but in practice, we don't think this is the case. So being more precise with the torus of AGN, we think it's clumpy, which means that it's more or less like in that picture. So you have these denser regions, denser clouds of molecular material. So the temperatures are low, we can have molecules there. If the temperatures are very high, the molecules are broken. Okay, and we have a lot of dust as well. And this clumpiness of the torus eventually can allow us to see through it. Because if we've seen through several clouds, at some point you can see a hole in the clouds. No, it's like looking at the sun. If you are under a tree, no, eventually you can see some flash. No. Okay. Let me see what I wrote here. Composed mainly of silicates and graphite. Okay, this is very interesting. The inner edge of the torus is limited by a physical reason. It cannot come closer because it will sublimate under the intense radiation coming from the accretion disk. Okay, so this inner edge of the torus is just evaporated, sublimated. Okay, due to the very high temperatures, and the emission coming from the torus it basically converts X-rays and ultraviolet photons coming from the accretion disk and re-emits everything in the infrared. Okay, this is thermal emission in the infrared. Thermal, like a blackbody emission. Okay. And the size of the torus, it goes typically from 0.1 parsec to 10 parsecs from the central black hole. And as I told you, it may have this donut shape, but we think it's clumpy. It's subdivided in these very dense clouds. Okay, this is a very interesting piece. This is a very interesting observation. This is a direct observation of a torus with the Hubble Space Telescope. This is the only one I ever heard about of a direct observation. Okay, and so we have this galaxy here, the NGC 4261, and this has jets. This is a radio galaxy, and if you look with the Hubble Space Telescope at the very center of the galaxy, you see this thing here, and this took me actually a long time to understand what we were seeing in this picture. But this is in the optical. This is it was observed with the Hubble. So this is the major piece of information you have when you're trying to interpret this picture. And where is the torus in this picture there? So we are seeing something that looks like a torus, but we see some bright spots, some dark spots, some inner dot. What I just said about the torus, it's made of molecules and dust. Is it colder or hotter than the accretion disk? Colder than the accretion disk. Does it allow light to cross it easily, to easily cross it? No? No, do you remember the type 1 and type 2 AGNs, no? Type 2 is exactly because the torus does not allow that. So the torus is the dark, the sort of dark biscuit in the center of this image. And in this bright dot here, we should find the accretion disk and at some point the black hole. Okay, so even if the resolution of a Hubble Space Telescope is extraordinary, we can see the torus, but we cannot see the accretion disk. Okay, it's very, very small, even for Hubble. What do you mean? Oh, what do you mean by point of view? I don't know. No, don't worry. No.
I'm not even sure. I'm not sure what we're seeing. Like,
So this panel here, it comes from a very small square here that the resolution of the screen here doesn't allow you to see. Okay, so it's just a zoom in the very center of the galaxy with the Hubble Space Telescope. I don't know which band, probably a near infrared band or a red band, I don't know. But yeah, this is a zoom at the very center of the galaxy.
the torus is the black region, not the white region.
Yes, the black one, the dark one.
What is the rest of the region?
Stars. It's the central part of the galaxy, like the core of the galaxy. And you see that this is the same orientation, so you see that the jets, they are perpendicular to the, well, at least more or less perpendicular.
Going out from the center,
Hmm?
is the beginning of the jet. Or not?
You mean this, there is some sort of cone here?
Yeah.
Yeah, I don't know. You see, we'll see now in some slides, you see the narrow line region, and you see that it looks like a cone. But for me, it's more likely that this is the beginning of the narrow line region. However, I cannot tell you. The truth is that I don't know. But I doubt a lot that this is the jet seen in the optical. Okay? But the truth is that I don't know. Okay, let's go to the narrow line region. So the narrow line region consists of a low density ionized gas located relatively far from the black hole. Narrow lines, the dispersion velocity is very, very small. No? If we could see it, the narrow line region would have a very specific shape. Actually, you can see it, but this is part of the plot here, no? Part of the drama. So can you see that the narrow line region, okay, these clouds here in this figure, far from the black hole, they represent the narrow line region. Now, the emission that we see coming from here has to be emission that came from the center of the AGN, interacted with the clouds, and then was re-emitted in our direction. Okay, so can you see that we would expect a preferred geometry for the narrow line region? So there is the torus here. Actually, the torus, we expect it to be much larger than that, much like that. So we have a region like that. Can you see it? Does it make sense for you? So for you, no. So we have a lot of dust here. Imagine this disk is thicker, like in the previous slide, okay? We have a lot of radiation being launched from here in these two directions. So the torus is blocking this radiation, but above and below the torus is not blocked. So the high energy radiation being launched by the center of the AGN will freely go in this direction and in this direction. Okay, so the narrow line region, which has to interact with the light coming from the black hole, will be in this direction here. Even if there are clouds like this here, it will not be part of the narrow line region because it's not interacting with the light. It's being blocked by the torus. Okay, so the narrow line region is concentrated in these two cones around the black hole. Okay, now there is some clever way of seeing the narrow line region. Here we have the spectrum of an AGN, where this is a type 1, but it doesn't matter if it's a type 1 or 2, we can do the same. Okay, you see that the oxygen 3 line, which is a line coming from the narrow line region, actually it's coming, if we know that this line here is coming from the narrow line region, and we can tell that by the, for instance, by the width of the line, if we were able to observe this galaxy only at these wavelengths, then we should see directly the narrow line region, no? And that's what we do. We put a filter. For instance, this is an image also done with the Hubble Space Telescope with O3, actually O3 and H-alpha filters. So in this very center of the galaxy, if we pass this O3 filter, look what we see. We see these two cones of radiation. Okay, this is radiation coming from the narrow line region. Okay, this is the region that emits that very sharp oxygen 3 line that we observe. And there are other cases also, but this is probably the most famous one. Everything okay? Okay, let's revisit the unified model. Maybe I should have put this image before. Okay, but let's try to recap a little bit. What's the difference between AGNs type 1 and type 2? What's the major difference? The inclination. So type 2, we only see narrow lines, which means that we are seeing in the direction of the torus. Okay, we are not seeing close to the black hole. Okay, but there is a very clever way to investigate if the type 2 and type 1 are the same thing, just at different angles. Okay, supposing that you don't have the resolution to peer there. And this is, if you take, maybe it's better if I draw it here. We have in the next figure, but I prefer to draw. We have a black hole here. However, this black hole is covered, is hidden behind a dust torus. Okay, we are looking in this direction, so we are never going to see the broad lines. However, if here there are free electrons or even dust particles, it doesn't need to be a lot of dust like in the torus, just a little bit of dust, okay, or free electrons. Look what happens. The radiation being launched from near the black hole can scatter in these particles here and then go anywhere. Okay. However, this scattered radiation will have some polarization associated to it. Have you done the experiment during your bachelor of rotating a polarizer over a surface? So you see that the reflected light was polarized. Have you done that, Anna? So the same will happen here. So if you take the spectrum of this polarized light only, you're supposed to see the broad lines. Okay, this is Thomson scattering, so it maintains the energy of the original photon. Okay, so there is this technique called spectropolarimetry, which is just doing the this is the normal spectrum, but also taking the polarization at every single frequency. Okay, this is the normal spectrum of the galaxy. This is the polarization intensity, here in percentage, so about 4% polarization. And this is the recovered spectrum, spectropolarized. No? So you can see that where before we had only narrow lines, now we have these broad lines. And if you see, this happens because I'm, with the polarimetry associated to the spectroscopy, I'm able to focus, not to concentrate only in the light that is being scattered here. So this kind of measurement tell us that there are broad lines hidden in type 2 AGNs. We cannot see them directly, but they are there. Okay, and we can find it with the spectropolarimetry. Clear? So this is, I think this is by far the major evidence supporting this inclination issue of the unified model of AGNs. Okay. Alright, the spectra of Seyfert-2 galaxies reveal broadline emission lines. Remember, Seyfert-2 has only narrow lines. If you do it with polarimetry, spectropolarimetry, then you find these broad emission lines that are completely invisible in normal unpolarized light. So, which means that a broadline region exists inside type 2 galaxies. Okay, this I think this was the first measurement of this type, the galaxy NGC 1068. So we had this very narrow emission lines. When we take the polarization of this spectrum, we can see the polarized version of this spectrum. We can see this the appearance of these broad lines. You see that the noise here is much higher because we lose most of the photons when we do the polarimetry filter. And okay, based on the amount of Seyfert-1s and Seyfert-2 that we observe, we see that approximately 2/3, I don't remember, 2/3 of the solid angle around the black hole is covered by absorption, because 2/3 of the Seyferts that we observe are of the type 2. Okay, observed directly without the polarimetry. Okay, so we expect in this case of AGN here, this Torus is quite small, so it should cover 2/3. Maybe this one is a bit better. It should cover approximately 2/3 of the whole sphere around the black hole. Okay, now just to give you some notion about the sizes of that we are talking about. So for a supermassive black hole with 10 to 8 solar masses, the black hole radius has nearly 20 light minutes. Okay, the accretion disk is of the order of 1 light day. These are approximations. And for this mass, for a supermassive black hole, the broadline region can be as large as 60 light days. Okay, so much larger already than the accretion disk. While the dust torus, look how big it can become. No, so 3 light years. Okay, so we are jumping from days to 2 years, and then the narrow line region. This, yes. No. Actually, the torus can start much inner, much. It's like the size of the torus, like the crossing size of the torus. The diameter of a section of the torus. And the narrow line region.
What's the distance from the black hole to the medium?
So black hole. Accretion disk, and here we start the torus. This here we have of the order of a few light years. Okay, so it's the diameter of a section of the torus. Okay. And then the narrow line region that I'm putting here 1,600 years, but actually it can vary a lot. So it can be much smaller than that, or much larger than that. Some narrow line regions have basically the size of the galaxy. So this is a quite of a naive estimation of the size of the narrow line region. Did you mention something?
The narrow size, the height is the diameter of a section of the. It's like a cone.
Yes, it's the height of the cone. Yes. And then I put here to give you some notion of the size. The orbit of Neptune has a radius of 4 light hours. Okay, so the accretion disk of a supermassive black hole is already 5 times larger, general scaling, 5 times larger than the solar system, up to the truncating the solar system at Neptune's orbit, no? So it's quite big. AGN winds. So in the next days, you are going to do optical spectroscopy of blazars, and you see that some of them, the lines are not symmetrical. You can have these lines with a bluish wing or a reddish wing. Okay. In this case here, we see that the carbon-4 line, for instance, or a silicon-4, have this blue wing. Okay, they have this extra emission towards the blue side of the spectrum, and these are caused by outflows. So you have gas around the black hole. This gas is being blown away. It's mainly by the radiation pressure of the accretion disk. Okay, and if it's being blown away, if it accelerates with the radiation pressure, it will suffer a little bit of blue shift, and we'll see this blue shift in the spectrum. So a line that would be symmetrical around this point here will now present a wing. Okay, and you see that this wing does not happen to all emission lines, and this is a very crucial, very important information. Oh, I wrote a lot here. They are located close. Okay, so very close to the black hole, hydrogen is ionized. Okay, so you are familiar with the Balmer lines, with the Lyman series, right? We don't have Lyman alpha here, but you see Lyman alpha in the spectra you are going to analyze. And but these lines are lines from de-excitation in a hydrogen atom. Okay, if the hydrogen close to the black hole is ionized, you are not having these hydrogen lines. Okay, so when you see hydrogen lines in AGN spectrum, they cannot come from the very near vicinity of the black hole. They have to come from a larger region, much further away from the black hole. A region that is cold enough to have neutral hydrogen. Okay, so we can see the lines. And if these lines can be emitted only in regions very far from the black hole, they are not subject to this kind of to this very, very strong radiation pressure. Okay, so the hydrogen Baumer lines, they will be much more symmetrical. Does it make sense? Because close to the black hole there is no hydrogen. Okay, they are ionized. You see that we need. You see that the higher is this is a rule of thumb, but it has its exceptions. When you go closer to the black hole, you start to see these very ionized elements, like carbon-4, for instance. By the way, in astronomy, we have a horrible, horrible way of writing the names of excited elements. So, for instance, carbon-4 means carbon excited 3 times. I hate it. Okay, so if you have helium-1, it's neutral helium. Okay, helium-2 is helium ionized, 1 electron. Okay, so when I say carbon-4 line, it's an emission line of a carbon 3 times ionized. Okay, and be aware that if you remove 1 electron of 1 atom, its spectrum is completely different. Okay, so you cannot say, this is an emission line of carbon. This is wrong. Okay, because the emission lines of carbon are not the same as carbon ionized ones, which are not the same of carbon ionized twice, and so on. Okay, so carbon-4 line is the line of an element ionized 3 times. When I become the emperor of astrophysics in the world, I'll change that. Okay. Okay, low ionization lines like H-beta and magnesium-2, you can see this a lot in the Aegean spectrum, originate further out in the broadline region or in denser shielded regions where the gas is more virialized. So its motion is dominated by gravity and not by the radiation pressure. So we would see the lines more symmetrical. Even if they are broad, they are symmetrical. Okay. They are, for instance, magnesium-2. We can see it as a broad line in Aegean spectrum, which means that it's relatively close to the black hole. Okay, so the Doppler shifts caused by the orbital motion will make the line become larger, but they are not very, very close to the black hole. Otherwise, magnesium-2 is ionized into magnesium-3 and 4 and so on, and the line of magnesium-2 that we observe disappears. Okay, so since we observe the magnesium-2 line, this magnesium-2 region is close to the black hole, but not that much. Okay. Okay. And the physics of the ions themselves detect how much they feel the light. For instance, carbon-4 is a resonance line. It's the excitation line. No? It's not a line coming from the capture of an electron, okay, by a carbon atom. It's a line of the excitation inside the carbon ionized 3 times. Okay. As a resonance line, it's incredibly efficient at trapping radiation and acts like a sail. So it every time it captures a photon, it gains a speed boost. No? This is, I already told you. magnesium 2 cannot survive in the inner region of the broadline region. Something that I must tell you also is that these lines, they are not just, they do not just present a wing. They present also a little bit of blue shift. So you probably are familiar with the redshift of the galaxies, but you have to be very careful if you are measuring the redshift, because if you take the carbon-4 line, for instance, or another high ionization element, you can measure it wrong. You can have a biased result for your spectrum. Okay, so if you are you are measuring redshifts now, if you want to measure the redshift, it's very important that you try to take a line of low ionization, especially hydrogen lines. Okay, if you take, for instance, the redshift based on carbon-4, since it's been blown away, the peak of the line will be shifted, will be blue shifted. Okay, so you have the redshift of the galaxy, but some of the lines can have a little bit of blue shift with respect to the systematic redshift of the galaxy. Okay. Okay. This is a bit tricky to understand if the emission lines that we are observing are coming from recombination or de-excitation. This recombination is actually, we can see it in helium. Helium is this, here you have carbon-4. Helium is this first peak here on the right of the carbon-4 line. Okay, so we can see that typically it is more blue shifted than the carbon-4 line. Even if the ionization energy is inferior to the carbon-4, but it's because it's coming from recombination. So you need to see this helium-2, you need helium-3, which is a helium completely ionized. So it will recombine and form helium-2, and then you see the line. Okay, you see here, this is the, how do I say, combined, composite quasi-spectrum obtained with the Sloan Digital Sky Survey data. And this is on the median, how we would expect the blazer of a spectrum of an AGN to be, okay? An AGN with an accretion disk like the Shakura-Sunyaev. Do you remember that the emission of the disk was growing with frequency to 1/3? Remember? There we were working on frequencies. If you convert to wavelengths, like in here, that solution is valid more or less up to here. Okay, so if you go to the inner edge of the disk, actually the solution is quite naive. But this is very useful for you. So if you are doing some observation of blazars and you want to separate what's thermal and what's non-thermal emission, you can subtract. You can subtract the, for instance, if your continuum here does not has this this inclination, it's probably because it's contaminated with non-thermal emission. So you can subtract the non-thermal emission until you see something like this. Okay. And that's, no, this is the, yes. There is one last thing, again, it's kind of random, but it's the Maddow plot. You heard about the Maddow plot, you do cosmology. What's the Maddow plot? Across the age, yes. Across, at redshift 2, yes, which is the same redshift where we have a peak on the space density of bright quasars. Okay, so we have this correlation between the, this is the Maddow plot. Okay, have you heard about it, Anna? Okay, this is a very important one in AGN physics. So coming from the beginning of the universe, redshift 8 or larger, the star formation rate was quite small. then it becomes very, very high around redshift 2, and then it starts decreasing again up to redshift 0, which is now. Okay? And something similar happens with AGNs. We have the peak of the space density of bright quasars around redshift 2. And this leads to a lot of research trying to understand what's the feedback of AGNs in the galaxies. Okay, if AGNs will stimulate star formation, if they will quench star formation, depending, it depends a lot on of the scenarios. Okay, but this is still a hot topic of research. Okay, and okay, bear in mind the Maddow plot. And that's it. What time is it? Okay, that's it for today. This will be the problem list. It will be the last problem list that of this kind, because for the other ones you have to do in the computer.